Okay, so today the goal, we're going to finish this, get through at least half of acids and bases, maybe even just finish the acids and bases chapter, but we'll see. I think it's a long one. So we'll see what happens. I am going to record this one, and I will actually post this one, because if we do go over super long, then you can watch. And then if you are in Wednesday lab because you have something on Monday nights, you can't stay after, then you can leave. I did want to recap real quick. So last week we talked about solutions, right? So molarity. Where's molarity? Well, using molarity to convert between, so like in a solution stoichiometry problem, you would have a volume of A, but you would also be given the molarity of that. And you can use that molarity to convert from volume to moles. And then use that to convert to moles of something else in your reaction equation. And then eventually find the volume of B. Or if you're given the volume, you can find the molarity because you have moles and volume. So we did a couple of those practice problems. So in this problem we wanted to know how many milliliters of this concentration of sodium carbonate would completely react with this volume of this concentration of nitric acid. So the way you set this up is you start with this 27 mils. You multiply that by molarity, because molarity is in units of moles per liter, and that gives you moles of whatever you're starting with. Then you can use the reaction equation and get your stoichiometric ratio, so then you can convert between one thing in your reaction equation to the other thing. And then by multiplying this by, really dividing by the molarity, you can get the volume of the thing that you're looking for. So those can look a little different. Definitely expect one of these on the last exam. At least one, maybe two. So then we moved on and talked about freezing point depression, boiling point elevation, these colligative properties, where it doesn't matter what type of solute you have dissolved. It just matters how many solute particles you have dissolved in the solution. So we can calculate freezing point depression using molality with the L there, and then using molality and a constant. Oh, well, this was calculating molality. So using molality, which is lowercase m, and a constant, we can calculate how much our freezing point will be changed from its normal freezing point. So multiplying molality by that constant, again, here we had 2.6 times 1.68, gives us 4.836. So our new freezing point is negative 4.836. Right, freezing point depression, so it lowers it. On the other side, we'll also get boiling point elevation. So the boiling point of a solution containing non-volatile solute is higher than the boiling point of pure solvent. In automobiles, antifreeze not only prevents freezing, but it also prevents boiling of that engine coolant in hot climates. So the formula is exactly the same. It's molality times Kb, so your boiling point constant. This is actually, I think, why you're supposed to add salt to the water when you're making pasta, because the water boils at a higher temperature and it cooks the pasta a little faster. So if you don't add that salt at the beginning, then your pasta is going to be real al dente at the end of the 11 minutes for spaghetti. You just boil it like a minute or two longer. So different solvents have different values of Kb. So we want to calculate the boiling point of a 3.5 molal glucose solution. All right, so sugar water. So our change in temperature, change in our temperature of our boiling point is equal to molality times Kb. So if here our Kb for water is 0.512, and we have a 3.5 molal glucose solution, we just do 3.5 molal times Kb, 0.512. Those units are degrees C times the kilograms of solvent divided by moles of solute, which I should point this out again. Molality is moles of solute divided by kilograms of solvent, not the solution. So then our our delta T for the boiling point, 3.5 times 0.512. So that's going to make our boiling point, or change in our boiling point, 1.792 degrees Celsius.
Can you explain one more time, I'm sorry, why we're flipping this one? Because molality is for, what is this that we're finding? So molality is different than the boiling point?
So you mean why is this
Yeah.
backwards from this?
Yeah.
It's backwards, so when we multiply them together, those units cancel out. So
Okay.
molality is moles solute per kilogram solvent. So if it's
I wasn't sure if this was different than finding, do you get what I'm saying? Never mind.
maybe.
You can say no.
So this is degrees C kilogram solvent over moles of solute. So that's the same thing that we're doing here. So these cancel out, and all we get is...
Okay, that's what so you're just writing the N, so you don't have to write the thing. Okay.
Yeah.
That's what I was asking, because I wasn't seeing what it was canceling out. Do you get what I'm asking?
I see what you're saying now, yes. This is equal to lowercase m,
Right, okay.
which is why sometimes molarity can be confusing as well, because it's capital M, but the units of it are moles per liter.
Okay.
So if you're going to do calculations, or if you're trying to figure out how to do the math based on the units, it can help to write those units out rather than sort of obscure them behind a different unit. Okay, so then our boiling point now of this solution is not 1.792 degrees C, but it's, all right, it would be 100 plus 1.792. So we get 101 would be the boiling point of this new solution.
Where does the 100 come from again?
Boiling point of water. So regular boiling point of pure water at sea level, 1 atmosphere, is 100 degrees C. Okay. So that's boiling point elevation, freezing point depression, kind of the same thing, basically the same equation, you're just using different constants. I might ask you to calculate the boiling point solvent based on, well, here, let me just insert a new slide here and give you a quick example. Add page. So I might give you something like, a solution of water boils at 103.74 degrees C. Actually, I like this one better. So it boils at this temperature. The Kb for water is whatever we had on the previous slide, 0.512, I believe it was. What is the molality of the solution? So this is just another one of those Kb, or not Kb, sorry. delta T boiling equals molality times Kb. So the tricky thing about this question is you need to know that the regular boiling point of water is 100 degrees C. So you would say, okay, well, if the normal boiling point is 100 degrees C, then our delta T is not 103.74, but it's 3.74 degrees C equals M, which we don't know, times our Kb, which is 0.512.
So then we kind of just have to know to add or subtract that 100.
Yeah. I would give you this kind of question for water because 0 degrees C is freezing, 100 degrees C is boiling. Yeah.
And then will this always be in Celsius?
Yes. Because the units of Kb are degrees C, kilograms solvent per mole solute. Or I could give you the molality and say, what is the constant for this? Right? What is the boiling point constant for water? Or in that case, I suppose I would give you a different solution. Say the normal boiling point is this. The new boiling point is this. The molality is this. Calculate Kb. All right. Osmosis. Should be familiar if you've taken much biology. So osmosis is the flow of solvent from a less concentrated solution to a more concentrated solution. Osmosis occurs when solutions containing high concentration of solute draw solvent from solutions containing lower concentrations of solute. So this is why if you're out on the ocean, you shouldn't drink the seawater, because the seawater has a very high level of dissolved solutes. Those solutes, when they flow through your body, instead of the water going into your body, it does the opposite. It actually sucks water out of your GI tract and dehydrates you more. So you can have water flowing through a semi-permeable membrane from a less concentrated solution to a more concentrated solution. Fluid will rise on one side of the tube until the weight of the excess fluid creates enough pressure to stop the flow. This pressure is the osmotic pressure of the solution. So if you set up these two solutions, this difference, zoom on this difference in height is how you measure the osmotic pressure, or one way to measure at least. Osmotic pressure is a colligative property. I think if anything for osmotic pressure, in terms of the exam, it'll be maybe a question like, what kind of property or what thing would affect osmotic pressure? So you need to know what a colligative property is, and that osmotic pressure is a colligative property. Basic type concept question. So as the solution becomes more concentrated, doesn't matter what it is, could be sugar, could be salt, could be anything, the greater is osmotic pressure. So the membranes of living cells act as semi-permeable membranes, and they allow some substances to pass through, but not others. So if you put a living cell into seawater, it will shrivel up because the osmotic pressure of the water, seawater, is so high. Reverse osmosis actually does the opposite of this, because they have special membranes that have holes that are just the right size for water, but nothing else. And so as you push water up against that membrane, the water slips through, leaves everything else out.
Quick question, it depends only on the concentration of the solute particles, not
Yep.
the type of solute, so what is that?
So you could have like a high sugar solution. I should move to this next slide. So if you have like a lot of sugar to a solution, that's going to have higher osmotic pressure. If you have the same number of particles, so that's why, I don't know if we use molality for this. Yeah, it could be molarity, I suppose. That's why we use moles though. So If you have 1 mole of sugar, that's going to have the same osmotic pressure in water, so 1 mole per liter,
Okay.
as 1 mole of salt per liter.
Okay.
Probably 1 mole of total salts. So, under normal conditions, you have a red blood cell. It looks like this. But if you put a red blood cell into pure water, because the inside of blood cells have a lot of different ions that mediate different processes, they will suck up water from that pure water, and they become all puffed up. But if you put a red blood cell into a concentrated solution, again, colligative property, doesn't matter what it's concentrated with, the water will flow out of the blood cells, and they end up looking not like red blood cells at all. So an isotonic solution is where the surrounding fluid is equal to that within the cell. A hypotonic is where the surrounding fluid is lower in solute concentration. So that's B. And a hypertonic is where the surrounding fluid is more concentrated, so the water gets sucked out of the cell. Cool. That is the end of that chapter. Are there any questions on solutions, colligative properties? I hope you're super comfortable with the idea of molarity, because it's going to come up a lot now. I mean, this is kind of like, we can go back to this even and look at, right? So up until gases, chemical bonding gases, even liquid solids and intermolecular forces, we were talking about really intermolecular forces for all of those, how things behave under different conditions. Now we're moving more specifically, like we talked specifically about gases, we're doing solutions specifically. So acids and bases is the next step there. I think Hank Green had a TikTok about this where he talked about how you can taste protons. That's what makes things sour. So acids, like citric acid, right? Lemons and limes are sour. Acetic acid and vinegar, which can make things sour. And tartaric acid, which is one of the acids used to coat Sour Patch Kids. So all these things are sour. We'll see why they produce hydrogen or hydronium ions later, but it's combining with your saliva that produces these positive hydrogen ions, and those react with proteins in your tongue, and we experience that as a sour taste. So, properties of acids. They have a sour taste. They dissolve many metals, which we saw with the producing the gas, where the magnesium dissolved in hydrochloric acid. Zinc will also dissolve in hydrochloric acid. And we have blue litmus paper, which detects acids. And when you dip it into, or when you touch it with an acid, it turns red. Opposite of it, acid still. So we have a bunch of these different acids. They're used for all kinds of stuff. Metal cleaning, fertilizer, plastic and rubber manufacturing, food preservation. You can add, I think it's ascorbic acid, vitamin C, to like apple slices to keep them from turning brown. You put a little squirt of like lemon, and it's the acids in the lemon that prevents like avocado or other things from oxidizing and turning brown. So carbonic acid, right? So all of these different acids, it's not like your typical Hollywood acid where it melts everything. Or like, have you guys seen Who Framed Roger Rabbit?
Yeah.
That movie's whack. But the vat of acid that they used to melt cartoons, well, actually, it's like turpentine. Anyways, it's paint thinner. So opposite of acids, though, we have bases. So bases have a bitter taste, and they have a slippery feel. And then there's blue litmus paper turns red in acid. Red litmus paper turns blue in bases. I think Yeah, we used not litmus paper, but pH paper. A little bit different. So again, huh?
What was the last one on the last slide?
Oh, red litmus paper turns blue.
Got it.
Yeah, we used pH paper for the one with all the well plates. Was that this class?
Yeah.
Oh.
Yeah.
I see how it travels.
Oh no, that was something else. Nope, it was a different class then.
I was like, wait, what?
It's like,
We
can't
got
remember.
ice cream?
Anyway, so like acids, bases are used in a lot of different things. I think especially cleaning products. I like this one, fantastic. Never seen that before. Drano, though, is sodium hydroxide. So, seen sodium hydroxide a lot in different just homework problems and stuff. But that's what drain cleaner is. And it just dissolves a lot of stuff. So bases are less common in foods because they're bitter. Don't generally like bitter flavors. A lot of alkaloids, which are bitter compounds, basic compounds, are found in plants, which are poisonous. So it's a warning to not eat them. And yet coffee, like a solution of coffee, is generally acidic, but caffeine gives it the bitter flavor. So there's a particular coffee called Death Wish that has like 700 milligrams of caffeine per cup.
Is that your favorite?
No, I haven't had it in a long time.
You have Death Wish?
No. So things like sodium hydroxide, which is used for petroleum processing, soap, plastics, potassium hydroxide. Sodium bicarbonate actually is one that we use in the lab, which you have on the counter, which I think is the baking powder, right? And so it neutralizes acids because it's a base. I believe sodium hydroxide is also used for canning as lye. So that's the same thing there. So we're going to talk about a couple different definitions. The first one is the Arrhenius definition. By the Arrhenius definition, an acid is anything that produces hydrogen ions in an aqueous solution. So while HCl is a covalent compound when it's by itself, as soon as we add it to water, it's a strong electrolyte, and it completely dissociates into H plus ions and Cl minus ions. So because it produces these H plus ions, according to the Arrhenius definition, it's an acid.
Is that incorrect or something? The way you're talking about it just...
No, well,
Oh, okay.
we have a better definition. So like this isn't going to change with the next definition. It's mostly the definition of bases that's going to change. So this is
Okay.
correct. This is fine. We just refine it a little bit with the next definition. I was just waiting for people to write stuff down.
It was the way you said it, so I was
Mm.
wondering. 'Cause I know there's some that were like proven wrong after,
Yeah, this one's more of a categorization. So these H plus ions are highly reactive in aqueous solution, and they'll bond to water, according to this reaction, to form, well, this is the hydronium ion. So in water, there's never actually a free hydrogen floating around. It's always bound up with water. So, and a lot of times, as you've seen already, we use these interchangeably. They both kind of mean the same thing. So when we're writing the molecular formula for an acid, we'll write that hydrogen first, right? We talked about naming acids and naming bases. But anytime this hydrogen is out front, that's the ionizable hydrogen. And that's the one that we can remove. So this one would, if we were to write out the ionization, well, we should do it this way now, H3O plus, and we'd get CHO2 minus. So we can't lose that second hydrogen that's part of that formula because it's not an acidic hydrogen. So the structural formula helps show us how the atoms are bonded together. We've covered that. And the molecular formula indicates the number of each type of atom. So this is the structural formula. So usually hydrogens that are acidic, in an organic compound at least, are attached to oxygen. So again, flip side of acids is bases. By the Arrhenius definition, and this is the one that's going to change, but you need to know the Arrhenius definition. It produces hydroxide ions in aqueous solution. So sodium hydroxide is an Arrhenius base because as a strong base or a strong electrolyte, it dissociates into sodium and hydroxide. Almost sneezed. So molecular compounds containing an OH group, though, such as methanol, do not dissociate in solution and do not act as bases. So primarily, the bases that we're going to work with are going to be things like sodium hydroxide. They're going to be ionic compounds. You can even have barium hydroxide. So you're going to have that metal first. I don't think there's any organic compounds that do that. So under this Arrhenius definition, acids and bases naturally combine to form water. So one is producing H plus, the other one is producing, one is producing H plus, the other one is producing OH minus. You can see that's together, 2 hydrogens and an oxygen, so we can form water. And we're taking this negative charge, combining it with the positive charge. The thing that the Arrhenius definition misses, though, is that there are some compounds, some substances, that when you add them to water, they act as bases even though they don't contain OH minus. And the Arrhenius definition can't apply to non-aqueous solvents. So the Bronsted-Lowry definition is the better definition. In this definition, an acid is a proton donor. So if you remember, hydrogen only has 1 electron. So if we take that 1 electron away, it has a positive charge, and it only has 1 proton. So these hydrogen ions that we're adding to solution with acids are just protons. So that stays the same. Bases, though, get their definition changed. Now a base in the Bronsted-Lowry is a proton acceptor. So anything that receives a proton in solution is going to be a base. So this applies to a wider range of acid-base phenomenon, and it focuses on the transfer of H plus ions in acid-base reactions. So now when we add this now we can apply this to things that aren't even aqueous solutions, right? It doesn't have to involve water. So HCl, easy enough. Bronsted-Lowry and the Arrhenius definition, it's an acid. Because in solution, it's donating this proton to water, and then forming this hydronium ion. So you have the Cl minus, H3O plus. So it's transferred from the acid donor to the water molecule, the acceptor, to form H3O plus. So in this situation, this is our acid. And then water now is our base because it's accepting that proton from the HCl. So this also works then, especially for ammonia. So if we add ammonia to water, it acts as a base. I was on that list of bases earlier even. But the way it forms hydroxide ions, the way it acts as the base, is it actually accepts a proton from water to form NH4 plus. Then those water molecules go on to become OH minus. So it's indirectly forming hydroxide, at least in an aqueous solution. And because it's accepting that proton, it's a base. And now water, because it's donating a proton, is an acid. So if acids are proton donors and bases or proton acceptors have to occur together because it can't donate the proton to nowhere and the bases can't accept protons from nowhere. So the proton's always coming from something. It's always going to something else. So for HCl, which was our example before, all right, that's our acid or proton donor. Water is our base or proton acceptor. And for the ammonia reaction, ammonia is the base and water is the acid. So this also highlights another special property of water in that it's amphoteric. So from H2O, it can either accept a proton and become H3O plus, or it can donate a proton. Well, I guess if I write H3O plus there, it's going to be the same thing. Or it can donate that proton and become, there's the donated proton, OH minus. So when the equation representing the Bronsted-Lowry acid-base behavior of ammonia is reversed, so now we're going to flip that reaction and look at it backwards. NH4 is now a proton donor. So that's an acid. And OH minus is the proton acceptor, so that's a base. And this is what's called, it should be highlighted, a conjugate acid-base pair. So this is different from water, because water can be, from water, it can go either way. It can accept a proton from water, or it can be water and donate a proton. NH4 only goes back and forth. So you have NH4 plus, and then, all right, so this is the acid, and then NH3, this is the base. Generally, I think always, the reactant side is going to be your acid and your base. On the opposite side, NH3 here is the conjugate base, and H2O is the conjugate acid. So conjugate acid-base pairs, again, any two substances, highlight this again, any two substances related to each other by the transfer of a proton. So HCl is an acid, and it's a conjugate base with Cl minus, or its conjugate base would be Cl minus. What?
What's conjugate again?
Conjugate just means they're linked together. I don't know the exact definition of the word conjugate. Yeah, because you could just think of these as acid-base pairs. I think it's in the same reaction, right? So in this reaction, the acid, then the conjugate base is NH3, because it depends on the context. If this reaction, like over here, starts with NH3, now this is the base, its conjugate acid is NH4 plus. So it's specifically within this sort of back and forth context, the base and the acid can change depending on which one's the reactant and which one's the product. So again, to review, a base accepts a proton, becomes a conjugate acid. An acid donates a proton, becomes conjugate base. So those are your conjugate base, acid-base pairs. All right, so in each reaction, identify the Bronsted-Lowry acid, the Bronsted-Lowry base, conjugate acid, and conjugate base. So for A, which of these is the acid? I think it's H2O. No. One.
The acid?
Did I say acid?
Mm-hmm.
Yeah, which one's the acid?
H2O.
H2O. Yeah, so H2O is the acid. So that makes this, I think it's pyridine, doesn't really matter. This is the base, because going from here, going from the reactant side to the product side, it gains that proton. So it's accepting that proton, makes it the base. Water loses the proton, so that's the acid. So then which one's the conjugate acid? Well, conjugate acid is going to be paired with, right, it's a conjugate acid-base pair, so it's paired with the base. So this will be our conjugate base, leaving this as the, acid. Did I say those backwards?
All right, okay.
Will it always be protons we're talking about? It won't be electrons?
Protons. Yeah, electron transfer, that's a different definition of acids and bases that we don't talk about in this class. Those are
There's more.
Lewis acids and bases, yeah. Talking about transfers of electron pairs. Okay, so this next one is, or I guess, which of these is our base?
That would be the water.
The water, yeah. So that makes nitric acid, our acid. And then nitrate would be the conjugate base. And hydronium, the conjugate acid. So one of the common acid-base reactions is a neutralization. This is actually what we did in the titration last week. We were neutralizing the acetic acid with sodium hydroxide from our burette, or, well, you guys were from your burettes, to get to the point where these two were equivalent. Well, except acetic acid. In all of these reactions, though, we get an acid reacting with a base, and we get a water and a salt. So in a neutralization reaction, we always form water and a salt. There are other acid-base reactions. And then the net ionic equation here, right, because this becomes H plus, Cl minus, K plus, OH minus. This, in solution, is actually K plus and Cl minus, because it's an ionic compound dissolved in water. So the net ionic equation is only the participating species or molecules. So because chlorine and potassium don't actually participate, we can cancel them out and say that really the only thing that's reacting is the hydride, the H plus with the OH minus to form water. So the salt is in there, but it's not part of the net ionic equation. We talked about these briefly as well. So you can also have neutralization reactions, particularly with bicarbonates, carbonates or bicarbonates, where you produce water, CO2, and salt, which, if you recall, is a gas evolution reaction. SO3 also does that. SO3, sulfite. So H3O phosphate. So we're going to write a molecular equation for the reaction that occurs between phosphoric acid and aqueous sodium hydroxide. So we've got H3PO4 plus NaOH. So what are our products going to be? This is an acid-base neutralization reaction. Water and a salt. And so here the salt is going to be made up of our cation from our base and our anion from our acid. Because that's when we react this and this. So we'll get sodium, and we need 3 sodiums because phosphate has a 3- charge. Oops, not 3. PO4. But then we need to balance this. So one of the tricks here is that if you have something like H3PO4 that has 3 ionizable protons, that's why all 3 of those are up in front, right, is the first part. We can also have, like sulfuric acid is H2SO4. So that can react with 2 hydroxides to form 2 waters. So you almost don't need to balance this because you can say I've got 3 ionizable hydrogens to react with 3 hydroxides will make 3 water molecules. And because I need 3 hydroxides, I need 3 sodium hydroxides, that also balances the sodium. Which is what this hint here is all about, right? Triprodic, meaning 3 protons. Any questions there? Keep on keeping on. So, acids dissolve many metals. You may remember the activity series, which we talked about super briefly. The activity series basically says if any, let's see, what was it? If any metal is higher than hydrogen on the series, then it reacts. I believe that's what it was. It's either higher or lower. I always forget. So these are metals that all react. You'll notice that. Okay. So we have hydrogen gas as a product of each of these reactions. And if you remember redox reactions, I'm just going to keep calling back to these random things. So our metal here has a 0 oxidation state. Over here it has a 2+ oxidation state because those electrons have gone to the hydrogens to form hydrogen gas. So in each of these reactions, we're oxidizing the metal, reducing the hydrogen to produce this gas. There are some metals that don't react also. So acids react with metals in a way that causes them to go into solution. So that's why when we had our magnesium dissolving to produce hydrogen gas, you dissolved it until the magnesium was all gone. And that magnesium went into the solution as magnesium chloride. And they usually produce, hydrogen gas. One of the trends, though, too, with acids and, particularly acids, is that they form a salt. So, right, our acid-base neutralization reactions produced a salt and water. Our metal acid dissolution reactions, I don't know if these have a specific name, will produce hydrogen gas and a salt. And we can also react with metal oxides. So if you react with the metal by itself, you get a salt, hydrogen gas. But if you react with the metal oxide, now there's also this oxygen that the hydrogens can react with. And when they react with a metal oxide, you get water and a salt, just like an acid-base neutralization reaction. Although you're not reacting with a base. So these are just some of the things that you need to be thinking about. Right? These might be like the different tiers of difficulty for questions. This is going to be like a mid-tier difficulty question where react hydrochloric acid with strontium metal. So part of this is, have a list of acids. So hydrochloric acid is HCl plus strontium metal. All right, one's solid, this is aqueous. So if we're reacting with a pure metal, we're going to get hydrogen gas plus, what's the other thing that we get? Strontium chloride. Strontium 2. Yeah. So then we need to balance this. So we have 1 hydrogen, 2 hydrogens. So if we put a 2, That'll cover our hydrogen and our chloride. So again, hydroiodic acid with barium oxide. Hydroiodic acid is Hi plus barium oxide. So now because we're reacting with an oxide, we have an oxygen for the hydrogens to react with. So we're going to get, instead of hydrogen gas, we get liquid water. And again, we get a salt, barium iodide. So this could be really any combination of acid. Oh, this needs to be balanced too. But this could be any combination of, strontium, barium, calcium, magnesium. Could even do aluminum or gallium, zinc, nickel maybe. Right, but really I could pick any of these metals, and I could say, react this metal by itself with an acid. You'll get hydrogen gas and some salt. If I give you some metal oxide, it doesn't have to be just one barium, one oxygen, or well, I guess in this case it does. It could give you magnesium or manganese. I could give you like Mn2O7, and then ultimately you just have to balance it because you're going to get water and a salt. So the base reactions aren't as numerous because the most important one is neutralization reactions, which we already covered. The only metal that really reacts that we talk about is aluminum in a solution of sodium hydroxide and water. And then you get sodium aluminum hydroxide and hydrogen gas. Don't worry about that one. Okay, so we did titration last week. This is the more of why that works. Because it's a combination of acid-base reactions and solution stoichiometry. So in our titration, we had a substance in a solution of known concentration. That was our sodium hydroxide, which was 0.1 molar. And then we also had a solution of unknown concentration. That was the acetic acid. So it's an acid-base neutralization reaction, and our net ionic equation is really just this. In some form or another. So if we wanted to do HCl, so if this is our HCl solution, the important part is not the chlorine, because it's a spectator ion. It's the hydrogens. So those are shown here for clarity. And let's say we want to figure out what the concentration of this is by doing a titration, right? Essentially what we did with acetic acid. We take our known concentration solution in the burette, and we drip it into the flask. And as we drip that in there, every one of these hydroxides finds a extra hydrogen that's floating around and reacts. And as soon as all of them are matched up, then we've reached the equivalence point and neutralize the solution, and phenolphthalein turns pink, which, as many of you saw, can take like 2 drops, and it'll be bright, bright pink. But at this equivalence point, that's where we'll see that these brackets mean concentration. The concentration of hydroxide is equal to the concentration of hydrogen. So we can use the known concentration of our, or not the concentration, I'm sorry. It's the moles and the moles. Right, the number of atoms and molecules, the number of particles is the same. So in the lab, we use phenolphthalein as our indicator. We knew the concentration of the sodium hydroxide. And then by using careful measurement of each of the solution volumes, right? That's why we use the burette, because it's very accurate at dispensing liquid. And that's why we use the volumetric pipettes, because they're very accurate when dispensing liquids. And repeatably, too. So this is what some of you saw. Some of you got even lighter than this pink color. So when we reach these stoichiometric proportions, it turns pink. We've covered that. It's just a special molecule. All right, so titration problem. If we're titrating a 20 mil sample, 20 mils of H2SO4 of unknown concentration. So the molarity, capital M, of H2SO4 is unknown. But when we do this titration, it requires 22.87 milliliters of our known concentration of potassium hydroxide. And that concentration is 0.158. So what is the concentration in moles per liter? Again, write this. Molarity is moles per liter. So what's the concentration and molarity of the unknown H2SO4 solution? You might be tempted to use M1V1 equals M2V2. Don't, won't work, especially on this problem. Because if we look at sulfuric acid, it has 2 hydrogens in front. It means it's a diprotic acid. So for every 2 moles of H2SO4, we're going to need, did that backwards. For every 1 mole of H2SO4, we're going to need 2 moles of potassium hydroxide. And you could get that too, or you could get that from a reaction equation too. You just write this out as a neutralization reaction. So our end goal here, we want to know the molarity of H2SO4. And we're starting with 22.87 milliliters of KOH.
I have just a really quick question.
Yeah.
0.158, that's moles, right?
Molarity.
That's molarity, okay.
Capital M is molarity.
Okay.
MOL is mole. Lowercase m is molality.
There's too many M's.
There's too many.
So what's the 27 point? I've got it, you're rewriting the equation of that.
Yeah, so this will be the solution diagram we're going to do first. So if we're starting out with mils of potassium hydroxide, what's our first step going to be? Convert it to liters. So we're going to go to liters of KOH. And then we'll use molarity. Yeah, moles of KOH. And then we know that because H2SO4 has 2 hydrogens to convert from KOH to sulfuric acid, which is our next step. We got to do a 2-to-1. Always run out of space. And then once we have the moles of H2SO4, we can use our known volume to calculate molarity because we have moles and we have liters. So I'm just going to rewrite this 22.87 milliliters of KOH. We can do one of these. And so each one of these arrows, we're going to be doing a conversion to the next thing. So if we want to convert to liters, 1 liter is 1,000 milliliters. And then we have we want to go to moles of potassium hydroxide. So we're going to use this. And remember, it's moles over liters. So if we want moles and we have liters, we're going to do 0.158 moles. Just writing KOH to remind you that's KOH, over 1 liter. And then to convert from moles of KOH to moles of H2SO4, that's where we need this 2 to 1, because sulfuric acid is diprotic. So we want moles of H2SO4. We have 2 moles KOH that needs to react with it. And then I'm going to take this 20 mils, and we can, because we're going to divide by 0.020 liters of H2SO4 solution. And that will give us molarity. So if we do...
We don't have to cancel the mole right there at the bottom?
No, because this will be... We'll get moles actually in this... Well, we'll get moles after this calculation.
Okay.
So then I'll put the moles up here, and then divide that by liters will give us molarity.
Okay.
22.87 times 0.158 divided by 1,000 divided by 2. So that's 0.0018067 moles. So if you divide that by 0.02, it's this doesn't seem right, 0.09?
That's what I got there.
That's what you got? Because we got milliliters, milliliters, liters, liters, moles of KOH. Well, we don't want to cancel out moles of H2SO4. Yeah, no, so that's it.
Okay. Where did you get the moles on top, the very last part?
That was the math from
The whole thing?
the whole thing.
Okay, got it.
Yeah.
And can you write the 1 mole H2SO4 to 2 moles KOH? How did you get that?
So that's because, right, so our acid-base neutralization reaction is H plus plus OH minus. But for every mole of H2SO4, there's 2 protons. So then we need 2 moles of hydroxide to react with those. Because each potassium hydroxide only has 1 hydroxide.
Are we also able to make a balanced equation just by reading the problem, or do we not have the information?
No, you could do that.
Oh, okay.
Yeah, so you could write out the balanced equation, right? Because you know you have... So yeah, if you wanted to find it by using the reaction equation, you'll get the same ratio. H2SO4 plus KOH reacts to form H2O plus K2SO4. So then you just balance this. So if we balance, I'm going to balance the potassium hydroxide, and we're going to need a 2 here as well. Wait. Yes, yes, yes. Okay, sorry. So again, there's hydrogens here. Yeah, so you can write out the equation if you want. All right. So we also not just have acids and bases, but we have strong acids we have weak acids, we have strong bases, and we have weak bases. So actually in the solutions and solubility lab where you had like the solutions to put into the light bulbs, or the acetic acid is actually a weak acid, and HCl is a strong acid. So that experiment didn't work out great, but you're supposed to see a weak light because it's a weak electrolyte. Hydrochloric acid is a strong acid, but hydrofluoric acid is a weak acid. So it doesn't actually completely ionize in solution. You look like you had a question.
Sorry.
So HF, hydrofluoric acid, may be a weak acid though, but it's also just like one of the worst acids because it will replace calcium in your bones and cause a lot of pain. And it will also eat glass because the fluoride ions have a higher affinity than hydrogens do in that glass structure. So they'll just rip it apart. Or then, the oxygen. So while we would get
Is that in like foods and stuff, or?
hydrofluoric acid,
Yeah, like
No.
how would you know that it eats bones? Just testing the calcium in your bones.
I am sure at some point a scientist made it, spilled some on himself, then had a really, really bad time.
Okay, I'm just curious.
Unfortunately, that's how that goes.
Yeah.
Not anymore as much. So strong acids completely ionize. This is where we talked about when you have these electrolytes. So you add them to the solution, and they immediately split. So these are hydronium, H3O+. They immediately split the hydrogen from the chlorine, and you get them separated in your solution. We'll talk about chapter 15 is equilibrium. But this arrow means that it's complete. So there's nothing that's remaining as HCl in the solution. Oh yeah, see I mentioned we talked about this. So concentration can also be represented by these brackets. That's our molar concentration of X, or our molar concentration here of hydronium. So if we have a 1 molar HCl solution, it's really 1 molar hydronium. Hydrofluoric acid, next slide then. So this was that experiment, right, where you have pure water, will not conduct electricity. HCl will conduct electricity, or hydrochloric acid solution. So these strong acids are mostly monoprotics, and actually the first proton for some other ones. So, they're all listed here. So these are all strong acids. You can find this table, 14.3. Sulfuric acid is a diprotic strong acid. So both of those will completely ionize in solution. There are some that don't. So the ionizable proton, again, is that first one. Weak acids, though, when you add them into a solution, they weakly ionize. So there's like a few of them. You get a little bit of that fluoride ion. And that's why we use this double arrow, which indicates partial ionization. We'll talk more about that in chapter 15. So they're also weak electrolytes, including acetic acid. So pure water, again, doesn't conduct electricity. A hydrofluoric acid solution, or any other weak acid, should conduct electricity a little bit. Not a lot, just a little bit. Which unfortunately I don't think worked really in the lab. But there are a lot of weak acids. So most carboxylic acids are weak acids. Hydrofluoric, I think, is the only binary acid that's a weak acid. We have acetic acid, which we used, formic acid, sulfurous acid, which is not sulfuric acid, right? So sulfuric meaning SO4. Sulfurous is SO3. Oh no, it is weak on its second ionizable. Whatever. It's not super important. We're not going to worry about that for this class. Just assume that both of them ionize. Carbonic acid and phosphoric acid, which phosphoric acid is actually in, well, a lot of dark sodas. It's bad for your teeth. All right, so which of these is a weak acid? Remember, weak acids hydrolyze only partially, whereas strong acids hydrolyze completely. So if we start with A, these purple ones are iodine, or iodide. These are iodide. This is our H3O plus. As you can see, so the acid that would have been added here would be hydroiodic acid, but we're not seeing any iodines that are combined with hydrogen still. So that would be a strong acid.
So that's what ionizing is, right?
Yes, ionizing meaning it's removed, or actually can be removed. So in the second one, we have nitrate. So this would be nitric acid, HNO3. And again, if we look throughout this, model of a solution, there aren't any nitrates. Well, there aren't any nitric acids left. So these are all nitrates. So this would also be a strong acid. This last one is formic acid. So it would be HCHO2. And if we look into the solution, this basically gives it away, but most of these are still protonated. I think there's this one that's not protonated. So it's had that hydrogen removed. So this would be a weak acid.
Now, since it's, because you said like partially ionizable, I
Mm-hmm.
know that's the next chapter, but that would be like partially ionizable?
Yeah.
Because some of it did break down, right?
Oh,
Or do you get what I'm asking?
yeah.
I'm off, I know, but.
No, it's yeah, partially ionizable is fine. Yeah, it's talking about ionizable just means can this hydrogen be removed? So in these other acids, like these are all have an ionizable hydrogen. There's not really a partial ionization, unless you
What was the thing
Yeah.
then?
multiple ionization, ionizable protons.
No, the little thing that you said.
Oh, the arrow?
Yeah,
This arrow.
partial ionization.
Oh, partial, yeah, because some of them ionize.
Right.
That's what it means by partially ionizable. So,
that
yeah.
would be that one, right?
Yes.
Okay. Sorry.
Yeah, it depends on how you're using it. Okay, so for these ones, we're not going to do the exact concentration in each because we haven't covered equilibrium. Wait, what is this? Interesting. Okay. So yeah, we're not going to do the exact concentrations because we don't know yet you guys don't know yet how to calculate the exact concentration of a weak acid. So first you need to determine which of these is a weak or strong acid. So is HCHO2 a weak or strong acid? It's a weak acid. Pretty much all the organic acids are going to be weak acids, if not all of them. So our concentration then is not going to be 0.50 molar H plus, but it's going to be much, much, much less than that, right? So there's going to be a small portion of H plus in the solution. We can't exactly determine yet. So then for B, is it a weak or strong acid? Strong acid, yeah. So what's our concentration going to be then?
Higher.
It'll be the same. So 1.25 molar, H plus. So strong acids completely ionize. And then for hydrofluoric acid, it's a weak acid. So again, it's going to be I guess the way I should have written this is the H plus concentration is going to be much, much less than 0.75. Let me fix this. All right, so there's going to be some concentration, but it's going to be small. Okay.
How are you getting that?
Weak acids only partially ionize. So it's going to be much smaller than whatever the concentration of the weak acid is.
So like if you go back on the little things,
Or the table, okay, got it.
yeah.
Oh, which one's a weak or strong acid? Yeah, the tables.
The tables, okay, so you figure that out through the tables, okay.
Yes. So bases can also be strong or weak. The difference, one of the big differences, I guess, between bases and acids is that when we have strong bases that have multiple hydroxides, they don't ionize step by step. So if we have something like H3PO4, which is triprotic, we can ionize this once, and we'll get PO4 minus plus a hydrogen. We can ionize that again and get HPO4 2 minus and get another hydrogen. And so it happens in steps. All of the first protons will be removed from all the phosphates before any of the second ones are removed, and then before any of the third ones. And it actually gets harder and harder for each one that you remove. For bases, that doesn't happen. It just goes straight from strontium hydroxide to strontium and 2 hydroxides. So sodium hydroxide is a strong base. As soon as you add it, you get that complete ionization. Weak bases, though, is analogous to a weak acid, so it's only partially going to, or it's only going to produce a small amount of hydroxides, or in the Arrhenius definition, and then by the Bronsted-Lowry definition, only going to accept a small number of protons.
What does analogous mean?
Analogous means, well, it's whenever you use like. This is like that.
Oh, okay.
So it's not saying that they're the same thing, but they're kind of the same thing, or the same in a lot of ways.
Comparable.
Yeah, it's an analogy. A weak base, right, is analogous. A lot of these weak bases actually produce OH by accepting protons from water. So ammonia is a weak base because it's accepting a proton from water to produce hydroxide ions, doing so indirectly. And this is just a generic for how that looks. So if NH3 is a weak base, again, we're only forming a small amount of hydroxide for all of the ammonia that we add. There are a lot of weak bases. Organic amines, so meaning mostly carbon compounds that contain nitrogens. So all of these, so NH3, pyridine, I was right about that, which is, C5. So basically, those are all carbons, these are all hydrogens. Has, in some ways, the same structure as NH3. I guess it's got 3 hydrogens on it. But each of these can pick up another hydrogen, and that's how they're forming bases. So all of these compounds, methylamine, methylamine is even more similar to ammonia. So you've got nitrogen, a couple hydrogens bound to a carbon that has 3 hydrogens. So ammonia, right, similar structure. So those all pick up hydrogens from water to form hydroxides. So similar to the other question, determine the OH minus concentration for each solution, right? So for strong acids, we're going to get complete ionization. strong bases, complete ionization. For weak bases, partial ionization. And then for, strong or weak. So is A a strong or a weak base? Strong base. So our hydroxide concentration is going to be 0.055 molar OH minus. Is B a strong or a weak base? I think in general, if it's nitrogens and carbons, it's going to be something like ammonia. So it's going to be a weak base. So our OH minus concentration is going to be a lot less than the 1.05 molar. And then sodium hydroxide is probably our most familiar strong base at this point, 0.45 molar OH minus. All right. So water is a special compound. It's amphoteric. It can act as either an acid or a base. Even in pure water, water acts as an acid and base with itself, which is called self-ionization. I think it's also called auto-ionization, but you have two different water molecules. One is a proton acceptor, the other one's a proton donor. You end up with your H3O plus and your OH minus. These happen, it happens, but it's a very, very small amount of the water that actually does this. So self-ionization occurs to a small extent, but you'll get equal amounts of H3O plus and OH minus because you have to have two water molecules for each. So if you produce it in H3O plus, you have to produce an OH minus. So they're always going to be in equal concentrations. And in pure water, at 25 degrees C, you'll have the H3O plus and the OH minus concentration be 1 times 10 to the negative 7. So that's neutral water. Let me see where we can take. All right. Finish the slide and then we'll take a break. And then I think we're just going to finish acids and bases. We've got, you guys can see it up there, probably 15 more slides. So probably another half hour or so, 45 minutes maybe. All right, so for pure water, 1 times 10 to the negative 7 for each of those. So the ion product constant for water, which is Kw, is our H3O plus concentration times our OH minus concentration, will give us 1 times 10 to the negative 14. That's constant. So actually, well, we'll talk about it in a little bit, but this 1 times 10 to the negative 7, that's pH 7. So that's neutral water. This 1 times 10 to the negative 14 is sort of a link between these two concentrations because they always have to be the same. So if you know the concentration of one in water, you can calculate the concentration of the other. Okay, yeah, let's take a 5-10 minute break. 5 minutes? And yeah, and we'll finish this off. I'm gonna bring any water. Okay. Saw an article for a research group developing a gum that traps coronavirus particles in saliva. Probably just,
For what does
yeah.
that mean?
So-
For a long time.
So basically, you would like,
So you don't have to wear a mask.
I
Your
think
gum
that's
is
the
the
goal.
mask.
Yeah, the gum would be like, so yeah, even if you had it and you're like not showing any symptoms, you go into a public place, just pop a piece of this gum, and then, because most of the transmission is from your spit and you sneezing or coughing or whatever, or even just talking. So then it would just trap all those virus particles.
What a time
But
to
then if
be
you
alive.
don't have it, do you open the gum or?
I,
Well,
yeah,
yeah, because you would still be breathing in and it would trap it just the same, right?
Yeah, so you.
that's interesting. Maybe.
Yeah, because that's what I'm.
In your, if you're a mouth breather,
What are you, you wanna hate on me or what?
because it's not going to trap it. You could like make plugs out of it for your nose. You're going to have an, yeah, antivirus particle nose rings.
Well, better learn how to breathe out of your mouth. Into your mouth.
Weird. Anyways, not the thing I expected to see in the news. Okay, so, right. Talking about water makes acid, base all the time. There's always, there's always this concentration of this or self-ionized acid and acid plus base. Right? So there's a balance between the two. So in our neutral solution, the two both equal 1 times 10 to the negative 7. In an acidic solution, we'll have more H plus from our acid than we would OH minus. So our H3O plus concentration is going to be greater. Should probably indicate this, right? So this is greater, the more acidic. In a basic solution, the opposite is true. We have more OH minus than we do H plus. So it's our basic solution. But in all aqueous solutions, those two concentrations, whatever they might be, have to multiply together to equal 1 times 10 to the negative 4. So if we know one of these, we can plug it in and we can solve for the other. So on the pH scale here, well, not pH scale, acidity versus basicity, we have our H3O plus concentration on top. So this is 10 to the minus 7, right? So that's 6 zeros before the 1. This is 7 0, yes. 10 to the minus 7 is 0.12345, and then the 1. So 10 to the minus 6 is going to be, let me move this a little bit. All right, that's 10 to the minus 7. 10 to the minus 6 is 0.00123445, and then the 1. So that's a higher concentration of H3O plus. So as we move this way, we get more acidic as our H3O plus concentration increases. And as it decreases, we get more basic. And then there's also a direct correlation between, as this goes down, this concentration goes up. So this goes negative 7, 6, 5, 4, so on. So those concentrations are dependent on each other. So let's calculate then the H3O plus concentration in each solution, and determine whether the solution is acidic. So we're going to use this 10 to the 14 equals H3O plus times OH minus. So if we take our equation, we go down here and we're going to say 10 to the minus 14 is equal to our H3O plus concentration. And then we can plug in this OH minus and get 1.5 times 10 to the negative 2. I guess right? And so we just solve for H3O plus. So we're going to end up with 10 to the 14, or if you're typing it in on your calculator, it can be 1e to the negative 14 divided by 1.5e. Nope, not that. 1.5e to the negative 2. So our H3O plus concentration will equal 6.67 times 10 to the negative, 13. And that makes sense because if this is a large number, relatively speaking, this has to be a very small number. And so it's kind of the same thing for all of these. So 10 to the minus 14 equals 1.0 times, or let me do this in the same order. H3O plus times our OH minus concentration, right, using this. And that's going to be 1.0 times 10 to the negative 7. We have H3O plus. So this will be 10 to the minus 14 divided by 10 to the minus 7, which will be 1.0 times 10 to the minus 7. And then the last one is 10 to the minus 14 equals H3O plus times 8.2 times 10 to the negative 10. So 1e the negative 14 divided by 8.2 e to the negative 10. So it's going to be 1.2, sure. Actually, 1.2 times 10 to the negative 5. So then we could do it the other way around too, where we calculate the OH minus concentration given any pH, or given any H3O plus concentration. So let's go through and determine now if these are acidic or basic. So for this first one, is 1.5 times 10 to the negative 2 larger than times 10 to the 13? Yeah, by a bunch. So this would be basic. For this next one, we've got 1 times 10 to the negative 7 is the same as 1 times 10 to the negative 7. So if they're equal, that's neutral. Because the concentrations are the same. And for this last one is times 10 to the negative 10 larger than times 10 to the negative 5. Nope. So this will be acidic. So in addition to using just the concentrations to look at things, we can also use the pH scale. So pH, I think it's calculated on the next slide, very similar. So if we have, we have an acidic solution when the pH, so pH is the concentration of hydrogen. When that's less than 7, we have an acidic solution. When it's greater than 7, we have a basic solution. And when it's equal to 7, we have a neutral solution. So you've probably seen there's like pH 8.5 or pH 8 water that you can get, which like is maybe good if you have like some acid reflux. But otherwise, doesn't do anything because your stomach is full of hydrochloric acid. So, I don't know. If you like it, you like it. That's fine. I don't think there's any benefit other than acid reflux. So the pH scale is a logarithmic scale. Actually, I'm going to point this out here now too. So pH 7, so pH 7 is the same as 1 times 10 to the negative 7 molar H3O plus. So we'll see how to do that calculation. It's not very hard. But this is the same sort of thing. So if pH 7 is 1 times 10 to the negative 7, pH 6 is 1 times 10 to the negative 6. So this mirrors the concentration. And so that's why if we have a lower pH, that's a more acidic solution, because this concentration is increasing. But it is a logarithmic scale. So going from pH 4 to pH 3 is not just one more molar or whatever. It's actually 10 more. So we've taken our concentration and now it's 10 times more concentrated. If you move 2 pH scales, now we've gone from 10 to the minus 3, 10 to the minus 2, it is now 100 times more concentrated than pH 4. And you can go down to pH 1, it would be 1,000 times more concentrated than pH 4. So a small change in pH is actually a huge change in concentration. I love this. Explain logarithms. Logarithms are kind of weird. So when you take the log of something, and in this case too, I do need to point out that if your calculator, so my calculator has this button that's ln. It's ln and it's log. So if you press it once, you get ln, which is the log, well, it's a natural log. So it's the log of the natural base. So that's log base e, which is a special number, is the same as, it's usually written as in cursive, it's the same as ln. But for converting pHs, we're using log base 10. So you can get a lot of questions wrong if you're using the wrong log. So the log of something like 1 times 10 to the negative 5, for example. The answer to this question is, what number do I have to raise 10 to get the number in the parentheses? So log base 10 of 1 times 10 to the negative 5, you have to raise 10 to the negative 5 to get that answer. So the answer is negative 5. Yeah, it's very confusing. So,
I don't understand a word you just said, yeah.
so what? That's why I said, it says explain logarithms, and it's like, that's a lot. Okay, so, yeah, I'm going to explain this. It's easy to use practically, because this is the equation.
Yeah, okay.
That's just, yeah. So I guess it's what exponent do I raise 10 to get this number? So this number being the number in here.
And you said it'll always be log base 10 in here?
Yes.
Okay.
Yeah, we're not using natural logs.
So literally it's just whatever, like if it was negative 6, it'd be negative 6, if it was negative.
As long as it's 1 times 10 to the negative 5.
That's what I mean.
Yeah, so as soon as we do something like, log base 10, I'm just going to write it out on this slide. I'm not going to write log base 10 every time. So if you have log base 10 of, let's do 5. 5 times 10 to the negative 5. I think I know what it's going to be, but I'm going to type it in anyway. So we got log of 5e to the negative 5. Nope, see, I'm always wrong. It is negative 4.301. But you can take your calculator again. So, I took the G.
So the log is specifically for pH on our calculators?
No, log is a function that's used in math a lot, or higher math. But in this class, we're specifically using it for pH, yes. If you wanted to go back to your concentration, you reverse this question. You say, well, if I raise 10, so we take 10, oops, that's the wrong one, 10 raised to the negative 4.301 will give me this number that I had over here. So I do that for, negative 4.301. Oh, I did that wrong. I need 10 raised to the negative 4.301. So then I get, there's a little bit off because of rounding error, but 5 times 10 to the negative 5.
So this is just like whatever it is to the sig figs, pretty much? Because like the 10 times the negative 5, that's like sig figs, right? Like,
Yeah, so this one, there were more. It's not even sig fig. Like the more
well,
digits that you
I
use, the
don't know
closer
how
you're
to
going to
say
get.
that any other scientific notation, I guess,
Yeah,
right? Yoda
I think so. Anyways, so for pHs though, we use the negative log because then we get positive numbers, and those are just easier. So if you wanted to get the pH, well, if you had a pH, let's say we have a pH of 6.3, right, that's our pH, and we want to know what the concentration is in molarity, then we would do 10 raised to the negative 6.3. And that will give us so our concentration would be, oh, nope, I did the wrong base. What the heck? 10 raised to the negative 6.3. This is 1, 2, 3, 4, 5, 6, 7. Would be 1 times, 5 times 10 to the negative 7. That would be the concentration of H+. So you do the negative log to get the pH. You use 10 raised to the negative pH. 10 raised to the negative pH equals concentration of H3O plus.
Whenever we write these, will it ever be like 5 point, how this one's 501 at the end, we won't ever do 5.01? Would it always just be a whole number?
No, you can do 5.01. That would be dependent on the sig figs.
Okay.
And then like for the exams, I'll tell you how many decimal places to give me. Yeah. Which is independent of the number of sig figs, just because I have to do it by decimal places for Canvas. So calculate the pH of each solution, indicate whether the solution is acidic or basic. So if we have 9.5 times 10 to the negative 9 molar H3O plus, then our pH is going to be calculated as the negative log of 9.5 times 10 to the negative 9. Negative log 9.5 E negative 9. So that is 8 point, well, so this would be 8.0 because of sig figs, and that's our pH. So a pH of 8, is that a acidic or basic solution? Basic. Because basic is going to be pH greater than 7. So this next one is the negative log of 6.1 times 10 to the negative 3. So negative log 6.1 E negative 3. So it's going to give us pH of 2.2. So is that acidic or basic? It's acidic. Because we have pH less than 7. All right, 8 more slides.
You can find out the acidic and the basic upon the chart, right?
Yeah, there's a chart for it. There was a slide for this. So yeah, 10 raised to the negative pH. I mean, we basically already did this, but that's going to give you back your H3O plus concentration from pH. So just as an example, if we have a pH equals 8.37, then we'll do 10 raised to the negative 8.37. I know there's a way to make this. Give me scientific notation. So it's going to be 4 times 10 to the negative 9 molar H3O plus. All right, so you can do all of those same calculations that we just did for pH with OH minus. So POH is the negative log of OH minus concentration. And we can reverse that the same way. So we talked about at the beginning of this sort of section that the concentration of POH, or not POH, sorry, H3O plus times the OH minus concentration is always equal to 10 to the minus 14. So we can take the negative log of all of these, because these concentrations are going to be small. So if we do the negative log of 10 to the 14, we're just going to get 14. And then one of the rules of logarithms is that if you have the log of, just for example, A times B, that's the same as the log of A plus the log of B. It's just like a math identity thing. So if we do the log of H3O plus, that gives us, the negative log of that gives us pH. If we do the negative log of OH minus, that gives us POH. Instead of multiplying these together, because of this identity, we add them together. So pH plus POH always equals 14. So if you have a pH, you can calculate POH. Just fill this in. So let's say we have a pH of 3.74 equals 14. So then 14 minus 3.74 I pressed the wrong button. 3.74 would be, left this off, plus POH. So 10.3 would equal POH. So we can calculate the OH minus concentration for a solution with a POH of 4.25. So for POH equals 4.25. If we want to go to concentration, it's the same thing as hydronium or H+. We'll just do 10 raised to the negative 4.25. And we'll get a concentration of 5.62 times 10 to the negative 5. But we could also, if we wanted to, find the pH from this. So, pH plus POH is always equal to 14. So 4.25 plus pH equals 14. We subtract that 4.25 from 14. Oops. And we'll get 9.75 as the pH. I think we talk about buffers, but we don't calculate anything for buffers. Okay. So the last slides. Buffers contain significant amounts of both a weak acid and its conjugate base. So the weak acid neutralizes any added base. The conjugate base neutralizes any extra acid. Human blood is a buffer. It's actually the carbonate or bicarbonate in your blood that does this. So in a healthy individual, blood pH is between 7.36 and 7.40. If blood pH were to drop below 7 or rise above 7.8, death would result because the acid concentrations would be too high or too low for the reactions that keep us alive to happen. So acetic acid and sodium acetate act as a buffer system. So you have the acetic acid. You can see that sodium acetate is just acetic acid with the sodium instead of the hydrogen. When acid is added, the acetate ion reacts. So we add this acid, it reacts with this base, and we form more of the acetic acid. But there's a lot of acetic acid present, so it doesn't shift that pH very much. So any acid in a buffer consumes any added base, and the base consumes any acid. So whatever you add to it, up to a certain point, it'll balance that out. So here they use these. All right, so if you add H, or if you add the OH minus, then we're able to balance those out. So the key for a buffer system is that you have a weak, was it weak acid or base? It's weak acid or base, right? Weak acids plus conjugate base. So H2SO4 and H2SO3, is that a buffer system? No. Not a buffer. HF and NAF.
Yes.
Yeah, because we have HF, hydrofluoric acid, which is a weak acid, and we have a conjugate base. So this is a buffer. I guess I'll write yes. Hydrochloric acid and sodium chloride. No, because we have a strong acid, even though we do have the conjugate base.
So it's only for weak acids.
Only for weak acids and only when they have their conjugate base. So then this last one, sodium chloride and sodium hydroxide, we don't even have an acid. So this is not a buffer system. So if you had something that was like hydrofluoric acid plus like a different weak base, ammonia is not going to be a buffer system because it's not the conjugate base.
Oh, so why isn't that oh, never mind, because then H would be attached, right? Or
Well, because, so like in this system, so the conjugate base would be sodium,
Yeah.
some fluoride ion,
yeah,
not a different molecule altogether.
right.
Yeah, okay. Yeah, see, we didn't go that far over. But that finished off that chapter, which puts us in much better shape